My name is George. Thank you for the invitation. I'm happy to be here with you, and I can see quite many participants. That's really nice. So let's move on quick to the topics of today. Of course, in our company, we do room acoustic simulations primarily, but as well as measurements. And we will try to address the importance of simulations in room acoustics, because in most of the cases, you cannot just get on with just putting a few panels on the walls or just using Sabine calculations, because things are more complicated. And then if you don't take that into account from the beginning, you will basically see the problems later on. And where we base mostly our, let's say, research and interface is on the ISO 3382. Of course, there are extra standards that we use, like the IEC standard about speech intelligibility and so on. But today we will look more closely at the ISO 3382, which includes most of the room acoustic parameters. Then we will navigate a bit into the audio and calculation principles, what kind of simulation models that we use, how we handle geometry import from other 3D modeling applications, and then we will give a short tour in the audio interface and have a conclusion with the most entertaining part, which is oralization. That is how you listen audio examples in your virtual models. You can basically listen any audio example from speech to music and make complex soundscape scenarios and share it with your customers. Right, so let's move on. The ISO 3382 parameters. The problem, if you consider the problem, is that everything has been developed all the last decades for measurements. So this is the guidelines we have nowadays. There is no standard for simulations, right? So that's what we have to follow. Everything we do in audio basically follows the measurement guidelines. And these guidelines for measurements can be how many sources and receivers you want during a measurement session, the heights of them, the distance between them or between the walls. And here I actually got a screenshot from our manual, which is also taken from the ISO, where you can see some common distances and some of the restrictions that the manual, the standard recommends when we do measurements. And we have three parts in the ISO 3382. We have part one that deals with performance spaces, like concert halls, operas, and theaters. And then we have part two, which is reverberation time in ordinary rooms, name it restaurants, classrooms. And then we have part three, which is open plan offices. That comes more and more common nowadays, like more and more companies introduce this type of working where you have big floors shared with many desks and then people working together, but you really need some concern about acoustics in all of these spaces. So let's focus up here in the title part one, which is performance spaces. And we can meet some of the common parameters as the sound strength, G, which is measured in dB, and basically gives us an idea of the amplification of the room on the signal due to the reflections from the walls. Because there's a big difference if I speak inside an auditorium than if I speak outside. My voice gets amplified inside an auditorium, and that's what this quantity measures, which is like an SPL parameter, sound pressure level, but simulated as if I had a source of 31 dB power level. Then we have clarity, which is defined either from the first 50 milliseconds of the impulse response or the first 80 milliseconds of the impulse response. And the first 50 will go for speech, and then C80 will go for music. They both basically measure, in simple words, how clear the signal is heard at the receiver. And here is an equation that basically calculates the energy that arrives between 0 to 80 milliseconds, if we're talking about C80, and then divided by the rest of the energy from 80 milliseconds and at the end of the response. So you can see that basically clarity measures what happens in the early part of the response divided by the late part of the response. If I'm in a room that has a long reverberation time, so it has a long tail in the impulse response, then the denominator will be higher and then clarity will be lower. So rooms with long reverberation time typically have lower clarity and vice versa. Rooms with shorter reverberation time, let's say in a smaller living room, have higher clarity because it's easier to hear each other. Then another common parameter is center or gravity time, which basically calculates the center of gravity of an impulse response. If we move on to part 2 in ISO 3382, then we have the different definitions of reverberation time. We all know that basically reverberation time is how much time it takes for sound to cease after we have a spark of sound. Let's say if we clap in a room, then we measure how long it takes for this clap to die. And that's the reverberation time. But in fact, we have different versions of reverberation time depending on how they are evaluated on the decay curve. We also have EDT, which means early decay time, and it's measured in the same way, but technically it's not a reverberation time because it concerns only the early part of the response. Here you can see this curve, right? So basically, if I evaluate EDT, I only evaluate the decay curve, which is here, the sound decay, from the early part, and then if I do this extrapolation, I get a different line. And the definition for all of the different types of reverberation times is when the sound goes down minus 60 dB. So when it goes from here it was about minus 27, minus 60 dB is about minus 97, and then that will be 1.2 seconds. If I evaluate it from a different part of the response, let's say if I go between minus 5 and minus 20, minus 5, minus 25, then I get a different, let's say, regression line from the curve, and that will define T20. Again, the definition is I have to find where this regression line meets minus 60 dB, and that will be in about 2 seconds. Here you can actually see on the right side how different reverberation times I can get depending on which part of the curve I use. When I use EDT, I get influenced more from the early part. When I use the others, I get influenced more from the late part of the response. Obviously, T60 is the true definition of reverberation time. So for T60, I start from the top of the curve and then I go minus 60 dB and it's here. But T60 is not something we use often because generally we don't have that enough decay range in our measurements. We have background noise and so on. That's why we usually stick to T20 or T30. That's not a problem in simulations because typically we don't have background noise in simulations, but as out of tradition, we use T20, T30 to be consistent with the measurement standards. Then we have part 3, which is open plan offices. And we define quite different parameters here. One of them is the distraction distance. It's the distance within the speech transmission index. The speech intelligibility stays above 0.5. And after this distance, goes below 0.5. Speech transmission index is basically measuring the clarity of the speech. So the higher it is, the better. Or you can say the more easy it is to understand speech. In an office, it's not always good to have enough speech intelligibility because you don't want to hear sometimes conversations that happen far from your desk. That's why you define these distances. If you are close to a desk and you can hear well what they say, then basically you have a lot of distraction. That's why you need to define the distraction distances. So you create a good acoustic atmosphere around the desks and also place your desks in a good distance between them so they don't distract each other. Same comfort distance, similarly, again, is defined from the source and defines where the sound pressure level A-weighted goes from 45 and less dB. So yeah, comfort distance is the distance again within which you have higher than 45, and then after that you have less than 45. Then another common parameter in open plan offices is the sound pressure level at 4 meters from the source for A-weighted speech. And when we're talking about speech frequencies, we're talking about 125 Hertz to 8 kilohertz. Then we have one fourth very common parameter, which is the spatial decay rate of A-weighted SPL. So how fast our voice decays per distance from the source in an office. And again, we need as fast as possible. So when we speak with a colleague, we don't disturb others that sit close to our desk. So you can see that all of these parameters, both open plan offices, reverberation times, are not easy to calculate by hand anymore. If I go one step back, you can see that somebody can argue we could use Sabine to calculate reverberation time. That's not the case in most of the rooms we have nowadays because Sabine cannot know anything about the location of the absorption in the room, cannot know anything about the geometry. It's just a formula that relates the volume and the overall absorption in a room. And in all of these cases, let's take, for example, an open plan office. You have so many coupled volumes. You have a volume here and then a small connection, and sound becomes far away from uniform. Let's say it's not a diffuse field anymore, and Sabine formula fails. So that's why we need a good simulation tool. And here I'm presenting Audion, and the next step will be first of all, to see how we can define all of these parameters inside Audion and calculate them. In the recent versions of Audion, you can see the formulas of all of the parameters, and you can edit and even create your own formulas for your own custom parameters. But how is everything calculated? We will see in the calculation principles. And the goal for any simulation in Audion is basically to derive the impulse response, which is the response from the source to the receiver. And basically, it looks like that, like this shape in the middle. And it gives the properties of the room. Because let's say the longer the response is, the longer the reverberation time, the bigger the room would be, very simple. And all of the other phenomena. But basically, an impulse response can be divided in the early part and in the late part. The early part is dominated by distinct reflections from the walls, especially the walls closer to the source and the receiver, while the late part defines the reverberation of the room and is very much affected by the volume and the absorption of the room. So for the early reflection method, we need something accurate and deterministic. So we use our image source method, we will see in the next slide. And then for the late reflection method, we use a more statistical model, and that will be the late radiosity method. And in order for Audion to decide where to start the late part, we just define a transition order. In this case, will be somewhere here in the middle. And from that part, Audion starts calculating the late statistical model. Before that, just a small introduction, how the reflections are defined. A specular reflection will be when we have a ray that is reflected with the same angle of reflection as the one of incidence, when the vertical is the reference. When we have scattering on the surface, then the reflected ray does not necessarily follow the same angle anymore. It can be any angle. And depending on the degree of scattering, the angle of reflection can be close to the specular if scattering is low, so if the surface is very close to a smooth surface. But if you have scattering of high value, let's say a rough surface, and to give an example, maybe like the virtual background behind me, these wedges in an anechoic room are very scattering because they stick out of the wall quite much and you have a lot of roughness. In this case, you expect high scattering and then the reflection close to random. Right? And Odion can calculate anything between them by building this zone of probability depending on the value of the scattering. Now, for the early reflection method, we use primarily a specular model, which is, as I said, the same angle of reflection as the incidence. And we use the image source method. In the image source method, basically we use the source and then we mirror it behind the walls. And then we draw a line from the image sources to the receivers to form the reflections. We have a first order, and then we can go as many orders as we like. We can keep reflecting behind the walls, and every time we reflect behind a new wall, the same image then becomes a next degree of reflection or order of reflection. We can see how it looks in Odion. We have the source here, and we have the receiver. And then we have an image source for the first wall that gives this reflection. And when we keep doing that for many sources, then we start getting the discrete reflections in the impulse response. It's these orange lines, with the red being the direct sound from the source to the receiver. It's not depicted with a line here, but it's as I show with my cursor. Right. The problem now is that this is only a specular model, so we don't include any scattering in the early part, but we remedy this problem by introducing some secondary sources on the same wall where we had the image source. And then these secondary sources somehow appear as a tail in the specular reflections. And you can see these green small lines. Somehow they smear the discrete reflections that happen from the image sources. And this is how up to 3 order image sources would look inside Odion, and the reflections with the green lines from the source to the receiver. And you can see actually here, depending on each color, what time they arrive, right? Initially, you have the direct sound arrives fast, and then you have the first order reflections arriving a little later, and then the green is much later because it's higher order of reflection. Part of the early part of Odion is also to take into account some diffraction around screens. Because in real life, waves travel around different screens and barriers. But we have to find some simpler algorithms to include that. And that's why we use the Alan Pierce's algorithm for diffraction. You can see some of the examples in this case. And here, if we get a sound color map, we can see how it be without diffraction. So anything behind this pillar will not receive any sound. But when we have diffraction, there is a little bit of extra sound coming. And also take into account anything behind this screen would be wrongly calculated without diffraction. But that's how it is inside Odion. Now let's go to the late part. And if you remember, that will be the part after the transition order in the impulse response. And we see a nice animation here. For the late part, we basically use our own custom-made ray tracing model What is ray tracing in tradition is basically shooting rays from the source to different directions and following each ray until it reaches the receiver. But as we'll see a little later on, the traditional ray tracing has some major flaws and some uncertainties, whereas what we do in Audion is basically that we track each ray, and every time it's reflected, we place a secondary source on each reflection surface. So after we shoot all of these rays, we end up having quite many secondary sources in the room. And a typical calculation in Audion would use at least 1,000 rays with times 100 reflections for each ray. So if we do this multiplication, we end up with 100,000 secondary sources. But it's very simple because usually we use even more rays than this one. Still, if we stick to this number, this is already pretty enough to give us an accurate rendering of the room of all the reflections that happen on the walls. Because then when we have all of this information mapped on the walls, we can basically gather that information to the receiver and calculate any impulse response and all of the acoustic parameters that we saw in the beginning. Yes, apparently we need to calculate the diffraction algorithm behind, let's say, a balcony like this, because not all of the secondary sources will be visible from the receiver because they are shadow. So only the visible ones will be calculated in the response. The nice thing is that still I use the same mapping of secondary sources and use another receiver without redoing the initial process of ray tracing. So every time I have the same source, I can just change receivers, as you can see here, right? And that saves me half of the calculation time. Yes, and very briefly to say that in the classical ray tracing, there were no secondary sources, and the contribution to the receiver was calculated by using a detection sphere around the receiver. And when rays intersected the sphere, then I could count it as a contribution to the response, but it would be arbitrary how big the sphere will be to detect the rays. So I could overestimate or underestimate the rays that hit the receiver. And for every new receiver, I had to repeat the process of ray tracing. And as you saw before, with using our customized ray tracing method, we have more accurate response because every contribution is calculated precisely from a secondary source to the receiver. And we build secondary sources with fewer rays, and then we don't need so many rays to make a detection at the receiver. And only the gathering part, like the contribution, is recalculated for a new receiver as long as the source is the same. So I save half of the time of calculation. So that's how a complete impulse response will look in Audion after taking the early and the late part into account. And as you can see, this will be the late part if we zoom this part in the full impulse response, which consists of the image sources on my left side, and then the rest part is calculated by the ray radiosity, the customized ray tracing method. Cool. Now, two slides only talking about the importance of scattering in Audion and the way we handle it. It's super important in acoustics because somehow I have to say that in room acoustics, we simplify waves as rays. So we saw already lines going from walls and from sources to the receivers, which is not really what happens in reality. It's a simplification. But since we don't model waves explicitly in our simulations, at least we have to include scattering as a parameter that includes all of the complicated wave phenomena that happens on the wall. And we saw before that high scattering will introduce a randomness in the reflection, and lower scattering will make it almost specular. But the same surface inside Odion can act as a scattering object if it's further away from the source. And that happens in real life too. Let's say you take your hand and you put it close to your mouth. It will send all the sound back to you as a specular object. Whereas if you take the same hand and put it 2 meters away from your mouth, then it acts more as a scattering object. And that is taken into account in Odion automatically, which eliminates a lot of guesswork, by the way, for your surfaces. And we have this animation here that shows that when the source was close, then the balls were reflected very concentrated with less scattering. Whereas if the surface goes far from the same, so if the source goes far from the same surface, then balls are reflected more scattered. Let's see it one more time, like this. And implementing all that inside Odion, we have seen through the years that we get pretty good agreement with measurements, because that's the whole point, how well we can predict reality. And here we have an example of a Rian Korsenhol in Sweden that was measured quite some years ago. And we see the agreement with some common parameters that will be EDT. Yeah, simulation is red squares and measurement blue X's. Now we see T30, reverberation time evaluated from -5 to -35 dB in the decay curve. Sound pressure level and clarity. Sometimes you can see some disagreement, especially at the lower frequencies. And that's, let's say, one of the limitations of room acoustics, that you have some limit or how low you can go in frequencies. In many cases, and many of the parameters, let's say if you take T30, you hit pretty well even at 125. In this case, I think there was not even, of course, a measurement at 63 Hertz. Yeah, you can see there's no data here. But depending on the size of the room, especially in smaller rooms where you have modes from waves and so on, which are not simulated inside Odion, you might see some disagreement in the very low frequencies. But the larger the room you get, the more modal overlap you have, and the agreement becomes pretty good. Now, a few words about geometry import. Odion is a room acoustic simulation software, so it's not the primal, let's say, tool to make your model, especially if they're complicated. And nowadays, our clients use a lot architectural software like Revit, AutoCAD, SketchUp. But we have made it possible to have pretty seamless importing from these applications, and even making possible to go back and forth, especially with SketchUp. And lately, we are very proud because we even made it possible to import, let's say, directly from Revit, IFC models, which are pretty complicated, and they have quite many different components that have to be simplified or discarded during the importing process. And Odion has pretty good tools for that. So in the past, if you attempted to export a Revit model as it was, it will end up probably something like the left image. But nowadays, uh, pretty automatically, you have a small interface that helps you doing that. You get a simplified model directly inside Odion and ready for room acoustic simulations. Because as we will see in the next screen, there is an important part here that we saw before. If we have small surfaces, they get more scattering. So generally, we don't favor models with small surfaces, and all of these triangles that come from the architectural modeling software. We like to have them simplified and, if possible, gluing the small surfaces together to form bigger surfaces. And this is also what happens automatically in Odion. If you try to to import a model directly from AutoCAD, let's say, without the simplifications algorithm by Odion, then in this case, you end up with about 1,362 surfaces. which is a lot, and you probably overestimate scattering. But then when you use the Odion gluing algorithms, where it glues the coplanar surfaces together, then you end up in this case with 200 surfaces, almost 1/6 of the original one. Right. Let's now see some fun part for the rest 20 minutes. That will be a tour in the Odion interface with some real examples. And for that matter, I would like to share my other screen and sound as well. Okay. And yes. Um, can you please let me know, him or Jeffrey, if you can see my Odion application? All there, right? Good. So here, I will start from the beginning. I have already started with a model in Odion, and the first screen we see when we import a model in Odion is basically the wireframe, which is the geometry in lines like this. That I can navigate with my mouse, left mouse button to rotate, right mouse button to move around. I can also use the space bar or the 3D view and then the options I have here for moving to the next view. And when I move to the next view, I can see it in different planes, also the floor plan. So by the way, this model was actually made in SketchUp, and it was pretty easy. We have a plugin that is installed in SketchUp, and it's easy to just press the plugin button and get the model inside Odion. But since there is a SketchUp model, I also see the SketchUp button here, which basically, if I click it, it will open SketchUp directly with the model loaded. I wish I had more time to show how the import process is done, but I think it's better if we stick to the actual workflow inside Odion once we have the geometry. So usually the first thing we do is either define our first sources and receivers or materials. And you have actually them in a sequence here. So here you have the source receiver list. Where you can see your sources in red spheres and your receivers in blue spheres. I have already a few sources and receivers defined, and in the lower half of the Odion window here, we see the source list, and then at the bottom, you see the receivers list. Let's say I want to define a new source. So I go at the end of the list, and I just click new point source button from the right toolbar. If I didn't have any sources, that would be just empty. Now it asks me to define a new source. I can give a description, new source one, and as you can see, the active one, the one I'm editing now, it's in purple or pink. If I start moving the sliders for the location, you can see this moves X, Y, Z. But I can also use the 3D view. And here I have a hint that says if you press Control and left mouse button, you can actually use the grid to locate your source in one of the nodes of this grid. This grid is just an aid, a tool that helps you locating your source. And if you rotate the model, it will snap to different planes every 45, every 90 degrees, basically, right? So here snaps to the, what is it, YZ plane. And you can do the same. If you control left mouse button, you can locate the source anywhere you want. But the thing is that you can now, of course, type a precise location and put it exactly where you want. You can also change the directivity pattern. By default, you have an omnidirectional source, which according to the standard is what you will use in reality when you measure reverberation time and other room acoustic parameters. But if you want speech transmission index, speech intelligibility, then you should stick to a source that represents human speech, normal or raised voice. And you can actually see the directivity is not omnidirectional anymore, especially if you go to higher frequencies, but it radiates more in front of the mouth. So that's why you have more sound in front. You can also choose other types of directivities like speakers from the market and so on. You can even define your own directivities, or you can put musical instruments. And here you see when you choose a directivity like that, like the raised voice, you can see the exact power spectrum that will help you calculating also the sound pressure level due to somebody speaking in the room, for instance. Right, the same way I can define a receiver, and I go down here and then I click the microphone button, new receiver. And similarly, I have a grid, but now I have a light blue dot that helps me localizing my receiver. A receiver is much simpler entity in a way that it acts as a omnidirectional microphone only. So there's no directivity pattern or sound power level or anything like that. It's just coordinates X, Y, Z. And during oralization, maybe I want to change the direction to point my ears where I hear the sound, but that's only for oralization. Let's say yes here to save the sources I created. I can close that window, and now we can go to the material list window, where we specify the materials on the walls of the room. And we talked about scattering before that controls the roughness of the wall, but of course, even more important is the absorption coefficient. So every material basically is defined by a series of absorption coefficients from 63 Hertz to 8,000 Hertz. You can see down here at the bottom, the value of the absorption coefficient for each material. And absorption means how much sound is dissipated inside the surface. When I have zero absorption, means zero sound is lost on a surface, so it's all reflected back. When I have 100 or 1, here is measured 0 to 1, it means all sound is absorbed. Yeah, so if when I have, let's say, a porous material, it typically absorbs more at high frequencies. And also I have colors that reflect that. I have a color code node that specifically describes the absorption property of the material. So in simple words, the higher absorption I have at higher frequencies, the warmer color I get, reddish, brownish. Well, higher absorption at lower frequencies, the cooler color I get. So blue colors for lower frequency absorption. And all of that together goes higher or lower in intensity depending on the degree of absorption. So the less absorption, the less opaque the color will be, as you can see here. And when I select a material from my right list, here is the default list of materials in Odin, which I can expand. I can also create my own materials from scratch. Then I can select surfaces in the model on the left side. And I hope you can see when it is highlighted by red, then I can just either say assign this material to this particular surface, and you can see this particular surface immediately got material 3021 as I have selected on the right side. But I can also use layers, so I can switch to the layer mode and assign materials on surfaces under a specific layer. Because imagine that you have, let's say, all the windows under a specific layer, then it's much easier to say glass for all the windows instead of going one by one. So here we have the walls, we have, let's say, the windows, and we can choose a material from this side and just assign it to all the windows of the room, right? Which is much faster. And same way, I can change the scattering coefficient, but keep in mind, since Audion, if you recall back, calculates some automatic scattering depending on the distance of the surface from the source and so on, it eliminates a lot of my guesswork. So many of the times, the default scattering coefficient is enough. Only if I do a strong simplification in my geometry, then I have to compensate with some extra scattering. And to give you an example, when I have a brick wall and I don't use all the gaps between the bricks and all the irregularities, or if I have audience and I don't model the people one by one, but model them as a big box, then I can raise the scattering coefficient to compensate for this lack of the detail in the model. All right, so now let's say we have assigned already quite many materials. We can have a look how the properties of the walls look if I go to the 3D render. And if you recall that a material follows a color code, I can immediately see that, let's say, the ceiling has high absorption and high frequencies, and the rest of the surfaces are harder and much lower absorption because it's not that intense. So this 3D rendering in Audion is not, let's say, a photorealistic rendering, but it shows the absorption properties of the materials. By the way, for this model, I also have, let's say, another version of the material list, which we call material archive. And if I switch back to this, then instead of having to open another version of the model, Audion just switches to another list of materials. And this list of materials has the screen as a hard surface now. So it's a pretty nice way to have this material archive and save different material configurations, up to 10, as far as I remember currently, up to 10 configurations. So you show your customers the different material scenarios. And the nice part is that you stay within the same project, material colors and so on. Within the material list, somebody could make a very fast calculation of reverberation time based on Sabine and other analytic formulas. But as you recall, I said in the beginning, this is only an approximation because it doesn't know anything about the exact location of the absorption and the geometry in the model. It just gives us a good indication of what happens in the room. But then, when we want more precise calculations, then we should go to the job list, which is basically, you can consider it like a spreadsheet where we can define different jobs, different calculations between specific specific sources and receivers. Let's say Sabine, or we actually have another tool called global estimation. This will give us an idea of the global reverberation in the room, but not per receiver, right? Yes, cancel estimate. Here, though, we have specific jobs, and you can see I just randomly select one of them. Job number 3, we have defined P3 saxophone as the source and receiver 1 as the receiver. So we calculate the response only particularly between these two. Now, we also have the multi-point response activated, which will actually calculate all the receivers defined in the model for the selected source. And that actually gives me some extra results, like some statistics between all receivers and so on. And finally, I can also do a very fast definition of a grid, which means basically I will select a surface in the model, and I will give a distance between these squares on this surface to calculate room acoustic parameters as a color map. Right now, we see just some random colors, and that's because it haven't been calculated yet. It's just how I defined it. But now let me just close this and go back to the job list. I also activate, let's say, the grid for the second job. So I will only run the second job in this case. I will run source number 2, which is the violin, and then I have a point receiver number 1, but I have also multi activated, which means also all the receivers for statistics, plus the grid all over the surface for a color map. So let's run this job. You can see real time, it takes only a few seconds, especially in that model, which is a small one, but Audion has a pretty optimized calculation engine, incorporating all the calculation principles I presented at the beginning of the webinar, which make it pretty efficient. So you can see even the color map, which has to calculate 531 color boxes. It uses this number of total arrays, quite many, about 2.5 million, and it takes only less than a minute. Less than, 50 seconds. Okay, but until this calculates, I think we can have a look pretty, maybe not, let's wait it to calculate. Maybe, yeah, okay, it's finishing in, okay, we are there. Yeah, we can start with the fun part, which is the grid. So to see the grid, I say view grid response. That's how we call the color maps. We call it grid because it calculates a grid of squares. You can call them receivers, basically. So all of these squares are calculated, and then Audion interpolates the values between them to give us a nice smooth color map. On the top right corner, you see the parameter, and we are in a particular frequency at 1000 Hertz. Using the keyboard arrows, I can change parameters or frequencies, up and down for frequencies, left, right for the parameters. It looks pretty cool, but also pretty meaningful. We see what happens all over the floor. In this case, always due to the selected source, right? And you can actually see that more precisely if I select the SPL, because apparently SPL will be higher close to the source. I use the spacebar to change views, and here we see a nice floor plan of the color map. A very nice way to communicate acoustics for clients and people that want to see how you calculated your rooms. And here we can briefly go to the multi-point response to see the results for all the receivers in the model. I could isolate some of them for the results here by selecting different groups of them, but let's just stick to all of them at this point. We see all the energy parameters for each receiver, but as I scroll down, I can also scroll to statistics between them. Let's see if I can. I have also these nice navigation buttons that help me jump directly to the section I want. So let's say for T20, I get an average of all the receivers, standard deviation, minimum, maximum. Everything can be exported from Audion to Excel sheets or Word files. I see them in bar graphs. I see the statistics in curves. And if I have measurements, I can also import them here and compare them side by side. Similarly, and more in detail, I can see results of a particular receiver, receiver number 1. And I see more detailed graphs like the detailed impulse responses for these receivers, the reflectograms, the image sources and the reflections, but as well as the impulse response. And in this case, according to the settings I have for my headphones and my head information, I actually have an impulse response which is filtered for left and right ear. And this can actually help me convolve, or let's say simply combine with any audio signal and listen how that audio signal would sound inside the room. So I can convolve it with a violin recorded in a studio or a speech recorded in a studio. And I say studio because actually, to be more precise, it has to be recorded in a room like the one I have in my virtual background, an anechoic room, because we want the recording to be free of any reflections. We only want reflections coming from the model to be included in the oralization. And this is how I will end the presentation, saying that you can make pretty complicated oralizations in Audion. Here we have the tab seed called oralization in the same job list, where we can select combining files in multiple sources and mix them together. So that helps us creating soundscape scenarios. In this case, we actually have a stage with musical instruments. It's a jazz band. We have violin, saxophone, bass, and guitar. We also have many sources scattered in the room producing sound effects like noise from jackets, from cutlery, from people speaking. And we have mixed all of that together to create an impression at different receiver locations in the room. So here, what you see here is the, do we have anything? Okay, I heard the sound and I thought it was a notification. Okay. So here we have the mixes of all the convolutions I have defined on the left side. And in this case, they are not calculated, but I think it's more fun if I jump directly to the example that we have uploaded online. You can all access that. I have given you the links in the chat. And basically, this is a newest app we have created, a web app. So somebody that owns Audion can export it this way and then can be uploaded or sent by a file to any user that doesn't have Audion, and you can experience the oralization yourself. So for instance, if you recall, I had two settings of materials in this room. One was with absorptive ceiling, the other one was without absorption, and we can alternate between these two scenarios. And I will also alternate between different positions and different mixes, one with the orchestra and the sound effects, and one without the sound effects. Let's have a play of it. I hope you can hear me. Let me know if you cannot hear the sound. We tested before, it should be there. Now I changed up the configuration. Let me actually go. What is it? Yeah, I'll play now without. Sorry, that was actually without the effects. Now I'll introduce the effects. And last sentence, I also send the examples link on the chat where you can hear some other situations like an open plan office or a concert hall with the same principle. It might take a few seconds to load the file on your browser, but then you're free to go and play different signals.
So off went the emperor in procession under his velvet canopy. Everyone
This
in
is
the
actually the same office I have used in the presentation as well, the open plan office. I don't want to go off time, so I think we should wrap it here and then go for questions, if him and Jeffrey agree.
Okay. Thank you, Josh, for your really knowledgeable presentation. Yeah, have it really thorough. And actually, we already got some questions from our audience, Ms. Jan, Louisa. Can you see the question, Josh, actually?
Yes, just to say
Yeah, in
now
the
that we
Q&A
start our Q&A, I don't know if we mentioned at the beginning, we have our director here with us, Klaus Lengen Christensen. He's the director of Audion since 2012, Klaus, 11, something like that. And he will be part of the questions.
Yeah, I think we have to repeat her question first because the other audience.
Oh, sorry, my bad. My
Yeah.
bad. Yeah, so let me explain the question. And
yes, I'm
from
reading
Luisa's
it now.
question is, do you have recommendation in setting number of rays for different room size, like classroom, 60 people open office, or a semi-outdoor space for pawn source and pawn receivers? This is her first question. And second question from Luisa is, Audion has pretty good correlation between simulated and modeled result. How about outdoor or semi-outdoor modeling? Yeah.
Klaus, would you like to address this question? You answer yourself.
So let me see.
Yeah. I mean, for the first part, I would say maybe Klaus, especially the second part, I would like you to be involved about the semi-outdoor modeling part. But for the first part, I would say that basically before you do any simulation in Audion, you go to your room setup. It's this interface that helps you defining the number of rays pretty automatically, again, as a function of the volume of the room and the absorption you have already given. You can see you have some options where you can somehow predetermine the number of rays. It's like a recommendation. So if you click engineering, then in this case, in this bar, gives 1,000 rays. But if I go precision, it jumps to 16,000 rays. You can type anything between them, but here it gives you a good recommendation. And I would say it doesn't really go, per style of room that you have a specific number of rays that you use. It goes really by case. You start with this preliminary numbering, and then the best way is after you do your first calculation. Hold on. Yeah, I can run this one. You can see specifically the decay curves of each receiver and see if you miss some energy in the part of the decay. Usually when you don't have enough rays, you will see the decay curve having a steep slope at the end where it clearly shows that you miss some energy. Let me show you immediately. I think it will be easy this way. Cancer. Okay. Yeah. So when I go to the decay curves, that's not so bad, but yeah, it is a bit bad. You see, I have these jumps here of the curve. It should follow smoother and continue from the early part. So I miss some energy in the late part. All of this sketchy line doesn't indicate that I've used enough rays in my model. And then the other question, yeah, Klaus, we don't hear your microphone, Klaus.
Hello, can you hear me?
Yes, we do
Okay.
have measurements with open plan theaters, right? That
Yeah.
have pretty good
Yeah.
correlation.
To just wrap up the first question with checking the results. So Audion does suggest some number of rays, and it does that depending on the number. So how long the dimensions of the room are. So if it's a very long room with very far-away surfaces, it depending on the dimensions of the room. So it's not an arbitrary number that suggests. Uneven distribution of absorption in the room, you might need more rays, and then that is the case where you'll get these jigsaw curves like George just showed. So we also, as I was about to say, we do have some extra rules for checking the quality of the calculation. So this screen is on, right?
Yeah. No, this screen is on.
Yeah. So there's the C parameter, which is part of the vibration parameters, and it's a measure that's calculated from the decay, and it tells about the nonlinearity it's taken from the regression line, and if it's above 10 per mil, then it starts indicating there it might be some problem, and we can see here at the lower frequencies in particular that it's indeed above 10 per mil. So then you might look into the quality of your calculation and see if there's something wrong with the simulation, for example, too few rays. So that could be an indication. We have the same for measurements. For other reasons, it could be too poor signal to noise ratio during the measurement. So again, for measurements, you might also want to check this parameter. So that's about checking quality of results. We have such parameters. As to having the quality of simulations and measurements in rooms, it's an energy-based model, so it depends on having a number of reflections being present. So if you have a room with many surfaces, then ODIN works very nicely. And if you have very, very few reflections, then it might start decreasing in quality. Like if you have only a ground surface, then results outdoor, then results will not be very trustworthy. But if you are saying in a city square or between some buildings with multiple reflections going forward and back, then we have a population of reflections, and then ODIN starts to work quite well. So I hope that's kind of an answer.
Do we have any more questions? I don't see something now. No. Or no.
Maybe I have one question. Because the example you showed is like a classroom test setting with tables and chairs. Under a situation like this, just like a typical office environment, do we need to build all the furniture, like tables and like that in the model?
Yeah,
The model. Yeah.
Actually, in this case, the standard says more or less what should be included. So the standard part 3 of the ISO 3382 suggests you make your measurements in the room when it's furnished but not in use, not with people there. So that means that you should include things like tables and chairs. If you have things like a computer screen in front of your workstation, well, this is a very dominant surface that will indeed produce a very important reflection, and therefore that should also be included. But things like keyboards and small desktop loudspeakers and that kind of thing should not be included in the model. But table, computer screen, things like that should be included. And in particular, if you have dominant surfaces that takes up, say, a big opening angle in front or around the source or a receiver, then you should include it.
We actually have pretty extended guidelines in our manual, how you model rooms and how you model the different entities. And there are also like some rule of thumb, like surfaces shouldn't be smaller than 30 centimeters, which corresponds actually to a wavelength at 1000 hertz. So we don't like pretty much, you can see like audience. Typically when it's especially in a big room, you don't model the seating or the people, but just the books around the people. That's why then you compensate with some extra scattering coefficient to accommodate that the lack of detail. I wanted to say thank you to Luisa for the nice comment about the Soundscape app. we're happy to hear that it looks amazing, and that's exactly the purpose, to be able to communicate acoustics with clients that don't own or don't know anything about audio or acoustics, the technical terms. This is the big advance of oralization, that you can even hear the echoes and different problems without having to go down to equations and details. Maybe there is one more. No.
Thank
No.
you, George.
Okay, thanks for
And
that.
also, I would like to have one question about the simulation software. Yeah. If I'm just a layman, but I'm really interested in the acoustic simulation software before using or implement the model or something using the model. Any special skill or any special knowledge should I have to know before using the model?
Well, Odeon is pretty easy to use, but to really benefit from what it can do, you kind of need to have the understanding of acoustics and what is important and what isn't important.
To be able to interpret the results properly, by the way.
But you can operate it and get nice plausible organizations out of it pretty easily, and there's a short guided tour to Odeon, which is in the manual and in the demo version of the software. It's something that layman can kind of step through pretty easily without having acoustic knowledge, but again to really benefit from the results it can give, and to be able to interpret results and suggest meaningful materials and so forth, you need to have the understanding.
But I mean, maybe it doesn't have necessarily, you don't need necessarily a master degree in acoustics, like even some technical web seminars, so you have a good knowledge about absorption and reverberation time. That we have people that, you have to be an engineer and get a good, understanding.
Engineers, architects.
Or architects, to get some understanding of acoustics. Maybe you don't need to know exactly how they're calculated. But some, preliminary, some elementary understanding of acoustics. And we also have, apart from Quick Start Guide, video tutorials that navigate through all the functions of Odeon, and not necessarily only about Odeon, it's also about acoustics in general, and some pretty useful articles on acoustics. You can see on our screen what is room acoustics, oralization, restaurant acoustics, which is somehow an easy reading, I would say, for most people as laymen, as you said, Jeffrey, or people in the industry.
And you also mentioned that in your website you have a demo for trial, right?
Yeah.
Available for download, yeah.
You can try Odeon for free, unlimited time. The only limitation is that you use the specific rooms installed, but there are quite many, maybe 20 more, 30.
Yeah.
Quite many different styles of rooms. So, and you can do anything you want with these rooms. You can change materials, sources, receivers, make as many jobs as you like. You can export the oralizations from them. And the other thing was that was the new thing I remember in the last presentation. I also have these demos of the Soundscape app only, which is some more complicated soundscape scenarios that anybody can go and play and listen. Yeah, I don't see more questions, right?
Okay.
Yeah, I think everyone feel comfort with your presentation, and thank you so much for your presentation. And
thank you too.
This is a really fruitful and knowledgeable presentation for me. Yeah. And
thanks again for the invitation. I think it was pretty nice for us to present to all of you.
So thank you, George. Yeah. So if our members have any question about the Odeon software, I think just feel free to contact George.
And if you cannot find our emails, if you go to contact us, then you find our different emails.
for any questions you have, for sure, and even a contact form if you prefer this way.
Yep.
And yeah, you can also follow, maybe good to say you have our social media platforms, like we have Facebook page, LinkedIn page, you can follow us on YouTube. And feel free also to subscribe to our newsletter. I can't remember if it comes, sometimes it pops as a window, but otherwise you go to about newsletters and then subscribe to our newsletter. We don't really spam you, just send 3-4 newsletters per year with some useful information about our courses, our new versions, new tools. You can see how the newsletters look and if it's worth for you to subscribe. But I can tell you we have customers that actually ask us how to subscribe because we don't spam people.
Yeah.
Yeah.
Yeah,
So-
anything else to add? We can add that Odin, although it was just a presentation about simulations, it's a full
Yeah.
measurement software, so you can measure most of the things which you can simulate in Odin.
And we even released a hardware piece 2 years ago. Basically an omnidirectional source, fully portable Bluetooth, driven with batteries, very light, 1.5 kilos. So basically replaces the need to carry a big dodecahedron with you. Yeah. Okay.
And thank you so much for tonight. And I wish everyone have an enjoyable night.
Many
Okay.
thanks for the invitation
Thanks,
again.
George, for your information. I hope you have a good day. And
You too.
thanks everyone. Good
Have
night.
a good day.
Thank you for joining this webinar. Goodbye.
Bye
Goodbye,
bye.
everyone.
Bye.
Bye.
Bye-bye.